Hello, my name is Hilmy with Donna and Hector, and this video discusses the experimental exploration of the cooling effectiveness of tube shape and position during FDM printing. For context, 3D printers are getting fast. As hot filament exits the nozzle faster, it needs to be air-cooled faster to solidify. Without proper cooling, parts can sag and become inaccurate. For the scope of this video, we'll focus on tube friction, bends, and inlet and outlet heights, and their effect on head loss within a system. We'll first review fundamental equations relevant to this experiment.
Bernoulli's equation serves as the main governing equation to evaluate head loss in a system. Head loss is the total distance loss due to friction and minor losses, which arise from factors including pipe valves, bends, and other fittings. However, by assuming constant density, gravity, and pressure, the head loss equation can be calculated with the following three sub-equations. These components are height, friction, and minor losses. Height loss stands for the difference in height. Friction losses occur due to the roughness of the tube, and minor losses are due to bends. Friction factor F is calculated by interpolating into the first figure the relative pipe roughness and Reynolds number. Coefficient K is calculated by using the radius of curvature to diameter ratio and the angle of the curvature, which can both be obtained with the figure on the right. First, we have the vertical tube, whose head loss is affected by the height and intrinsic tube friction, and has a calculated head loss of 3.5 meters. The only loss experienced by tube 2 is an increased roughness inside the pipe. Using the previously calculated head loss, we were able to solve backwards to calculate the roughness of the dips and create an equivalent head loss. Lastly, we have the bend tube. This one experiences head loss due to friction and minor losses due to bending. We first calculated the curvature coefficient and solved for the minor losses. Afterwards, we find the required length of the tube to create an equal head loss when compared to the other two pipes.
In terms of designing and manufacturing our showcase of head loss, we dug around for a little bit and found surface roughness data on resin prints, a likely candidate for manufacturing due to its repeatability and accuracy. At the Invention Studio, their resin 3D printers have a maximum build volume of 145 by 145 by 185, so we decided our longest tube, the one exhibiting height, would be 145 millimeters in length, with the other tubes being shorter. In terms of measuring airspeed and keeping the apparatus relatively affordable to make in a reasonably sized package, we decided to make makeshift anemometers, with turbines inspired by turbochargers and IR sensors measuring RPM. After a little bit of manufacturing, which included traditional FDM 3D printing, resin printing, water jet cutting, metal brake bending, press fitting, soldering, coating, and testing, we made a thing.
The experimental setup includes 3 different iterations of a duct tube with a distinct feature that contributes to the overall loss. The first tube has a straight, smooth structure with different inlet and outlet heights. The second tube has interior roughness, and the third tube has a bend, although the last two maintain the same inlets and outlet heights. A fan connects to the base of these tubes to provide airflow, which a self-assembled anemometer measures at the top of the tube. By utilizing a circuit board, wiring, and a lab-manufactured turbine apparatus, the rotations of an indicator on the turbine will be tracked by the device to measure the exit velocity as air flows.
Unfortunately, we couldn't get all of our anemometers to work and prove that the airspeed could be the same for visually distinct tubes. But this was still a fun exploration of fluid mechanics and its practical applications to additive manufacturing. Moral of the story, keep your tubes as straight as possible and as smooth as possible. Thank you.